So good morning, guys. About 60 people have joined, and we're waiting for some more to come. But we will not wait too long. Now, today, what we're going to do is today is going to be the last of the back propagation series, that is forward propagation and back propagation series. Next week onwards, we will start doing programming with PyTorch and all that. Whatever we have done, this was basically to build a theory which we will implement in PyTorch and show you how it gets implemented. Rest of it, of course, this code is always there, and this code can be tried and done. And as we are doing, we are also showing you the code, and you can also create code on ChatGPT. See, nowadays creating code is not a big deal, so we are not emphasizing that. Understanding that is far more important. So I'm spending a lot of time trying to elaborate or make you understand the code. I think some of you are getting it, some of you are not. I think obviously those who are going to get it are going to have a good journey through the AI cycle, and those who don't, well, we will see what to do. Uh, so, if you recollect, the story so far has been in the earlier sessions, we talked about how to build a small neural network. We'll continue with that neural network. In fact, today's session may not be too long because it's just a conclusion of the backpropagation series. We call this a backpropagation series because that's what they focus on basically calculating the gradient and all that. So if you remember, we had taken a very simple example all through the last few weeks. We had talked about the following. The topics which we have covered so far is we will just give you an overview. So one is we talked about forward propagation. We saw how to create a network and do forward propagation. We talked about backward propagation with the stochastic gradient. That is the gradient was getting updated every time. So that was backward propagation. We talked about how to compute the loss function, and then how to take derivatives of the loss function and how to propagate that backward. And then last session we talked about the mini batch with back propagation, mini batch with backward propagation. Uh, And today we are going to talk about two small things, which are basically, if you have understood this, you have understood quite a lot. We are going to talk about momentum and learning rate decay. Uh, Learning rate decay. So we are going to talk about these two today, and these will mark the conclusion of these backward propagation series. So in the next session, I will take you to Tantric. We have done something in Tantric in the past, but we will have to do it more extensively and show you how all of this works with the GPUs and with PyTorch. So in the next session, I will transition to PyTorch, where you will see what we are representing for a neuron becomes so much easier. But to understand and really appreciate PyTorch and how the tensor works, basically, unless you have understood these sessions, it might be very difficult, or you will have a very superficial understanding of how PyTorch works, and that may not be good for. That may be okay even if you don't understand PyTorch. I see a lot of people programming, but it will be very shallow programming. Anything serious and deep, you will have to go through all these sessions, understand how this works, and then you can apply a lot of it. Okay. So we have that as a plan. So next week onwards, we will start doing a lot of lab work with PyTorch, with actually the ANN implementation. So I intend to finish the ANN implementation in with PyTorch in a session or two, I think it will take us only a session because we already know the theory. So for us to implement an ANN will be very simple. And then we will go to start the CNN, and then we will start the big AI. It will take time. We are going very slow. The reason is I want you guys to become perfect, and then we will have a very interesting story. I will also have to spend some time introducing terms like vanishing gradient and all that, but those becomes easier to understand once you know this whole thing. So before I start, let me ask you all, maybe for some of you, an embarrassing question, which is how far are you clear about the things that I expect you to be clear is the following. Uh, so how far are you clear about the following things? You know how to compute loss, how to compute that is a mean square loss, then how to take the derivative of the loss function, uh, and then how do you take the derivative of the loss function and how do you take it backward? That is, how do you propagate this derivative back using the delta? So how many of you have understood this delta that we keep using? And how is the update connected with delta? Okay, update to the weights. Update, when I say update, I am obviously update, I mean is the update to weights connected with delta or derived from delta. Then how the mini batch works. Why did we do mini batch? So that the we don't oscillate too much in terms of weights. We don't want to update weights after every sample. We want to watch a whole batch and then continue to update the weights. So we would last time we explained mini batch, uh, and then have you understood how to accumulate the gradient? Because here in the first case we had applied the delta after every sample. In the mini batch we accumulate the gradients. We accumulate the gradients for a batch and apply it after the batch is over. So how do you accumulate gradients and how do you apply gradients? This is what we did in the last session. So these are some of the things which any good AI engineer learning deep learning is expected to be aware of, expected to be knowledgeable about. This is the classic AI thing which is there. Now I'm going to pause here and ask you, how are things? How is it that uh, how far you have crossed? Okay, has all of this become clear? 1, 2, maybe 3, and 4. This is what I have been doing the last 4 or 5 weeks. So have you understood this? So I'm going to do a poll, and after that we're going to start. Okay, all of you are here. Please try and answer the poll. Okay, I think I don't think we'll get more than this number of votes. Okay, so looks like about 48 people, that is half the people, have understood something, and half the people have understood a lot more. Okay, anyway, see, today, as per tradition, I'll repeat to a certain extent what I did in the last class, because today's class is an increment on the last class. So I'll again walk through the code. But today is the last time I'll walk through the same code. And after that, we will go to PyTorch. So basically, uh, from the next session, we will not see this code. We will all keep in mind all the principles that we have understood here. They will all have to be useful. But we will move on to PyTorch. That's why it's very important that you understand this. Now, okay, so we have about 100 votes and we have a pattern. Okay, so I will start. Now, before I start, I told you it is, I promise that we will talk about the startups for a bit, what they are doing in this week. Well, nothing much has happened in this week. The startups are still coming up. So the real activity will start in the beginning of the next semester. So I think once they are all triggered and started, I'll have more to report about each startup. But having said that, I mentioned about eight startups, yes, in the last session. Okay, in addition to that, there is a ninth startup that we are also adding, which is very interesting. It's basically, packaging. I don't know how much of this thing you know. Okay, let me give a brief description of this ninth startup. It is in the packaging area. We were planning to call it a packaging paradigm. It is very interesting. Okay, I think you should start getting this domain knowledge also as you go. So this is a gist of our packaging paradigm, which is our nine startup. You know why we are calling all our startups as paradigms. So because they represent in many ways the application of AI. Part of the reason why we are starting all this, I think I mentioned it in the last class, is we are transitioning to become a university. At least the Uppal campus is transitioning into a university. So basically, as we transition into university, we want to make our university very different, very top class, because we'll have full freedom to set the syllabus, conduct the curriculum the way we want it, conduct the exams the way we want them, and all of that. So we intend to use this freedom to create world-class institutions. And today, world-class institutions are not world-class institutions if they don't have a whole startup ecosystem surrounding it. So unlike other universities in and around Hyderabad, our focus is on having a string of pearls. We call it a string of pearls. That is how I describe the startups which are coming around. So each pearl, so we have a ninth pearl, or the Navratna of our thing. The ninth pearl is in packaging paradigm. So to give you a brief background of what this is, it is like this. Okay. Now, I'll not spend too much time. If you are interested in more detail, you can research on your own also. It is like this. So, I hope you know what is chip making, right? The making of a chip, a silicon chip. Now, once a chip is made, it becomes a wafer. Okay. A silicon chip is wafer. A wafer by itself is of very little utility. It has no capability. I mean, it has to be packaged. Not all wafers are packaged, but some of the wafers are packaged. Some of the chip wafers are packaged. That is, they are mounted on appropriate boards, they are appropriate substrates, and then they go for production. I mean, as part of the production process. So, unfortunately, in India, we do not have too much of chip making or chip design business. We have some chip design, but most of the chip making is done in Taiwan, China, or other countries. We have somehow, because this requires very sophisticated technology, and but the packaging represents a very interesting opportunity, and there is various parts of the packaging which require a lot of AI. Just to give you a gist, some of the wafers which are produced, they will have to go through a camera. So a camera will look at them, and depending on the output of the camera and the AI which works on the camera, this wafer will be deemed fit for packaging. Okay, some of the wafers will be discarded. Now, this is typically a manual activity, and it obviously requires a lot of people with keen eyesight watching every wafer before it is to be taken into packaging. But this can now be done in AI. A lot of our factories a lot of factories worldwide have started using AI for watching the wafers, deciding whether its quality is deserving of packaging. Because if the wafer is not good, you unnecessarily package it, a lot of cost goes in, and which is a waste. Uh, and as part of packaging also, there are various steps which require AI. For example, is the when this wafer is put on a substrate, is the substrate correct on which it is mounted? So something has to check. Again, this is done by machine or manual, and again this is very slow. So this whole pipeline moves forward, and there are several occasions in the pipeline where AI is necessary. Currently, this entire process is manual, and it adds a lot of cost. Remember, I'm not talking about chip making. I'm just talking about once the chip is made, I'm just talking about the silicon packaging of the chip. And for that, there are quite a few companies in India, especially based out of Gujarat. Now, Hyderabad is trying to get into this space, and part of the thing is we will again not get into the wafer making space. That's too sophisticated. Even in Hyderabad, for specific functions, we'll do a lot of packaging, and this has an enormous application of AI. Now, I will probably, one of these sessions, I will give you a background of all the 9 companies, 9 startups that we are building, where I'll talk about exactly what we are doing. But this is just a gist of what we are going to be doing. And this is one of the, again, startups, besides the 8 startups that I mentioned here in the last class. This is again a packaging paradigm, and we are, it's part of one of the pearls of our string. It's actually a necklace of pearls, so we call it a string of pearls. And so that's what I am building. We are building as part of the the university ramp up. So that's the motivation. I'll give you updates on all the startups as they proceed, because all of them are extremely AI. All of them are AI, and all of them are domain AI, domain-oriented AI. So what I expect young people like you to be doing is basically, first, of course, you need to learn AI. You need to learn how the basic ANN works, the basic CNN works, the basic GANs, VAEs, and also then the generative AI, which is transformers, and the concept of diffusion, stable diffusion. How do they work? So once you go through all these basic algorithms, which I'm doing through these sessions, basically we'll take you to the domain-oriented AI, where we'll build models specifically for various problems, and we'll teach you how to build models through our I mean, those of you who are interested, obviously, will join these startups as in 2 as interns, and they will become part of these startups and learn how to actually use AI to do many of these stuff, whether it is a drug discovery, whether it is NOAA paradigm, whether it is to do with the women health, whether it is to do with material science. All this you will learn, and you will learn to apply and do. So that's will be the interesting part, and hopefully we will produce a lot of people who are well versed in it and who go up to do these startups. So these startups are actually supposed to act as the kernel of a startup. The way we visualize this is, we'll give you the kernel startup, then you may expect various aspects of the domain. This we will do, and then we expect you to specialize. Those of you who are interested in creating your own startups, you specialize and create your own startups based on the basic core startup that we have done. So we create the substrate startup. All our startups, whether they are there in drug discovery, whether they are there in feminine health, or whether they are in a neuro paradigm, that is autism and dyslexia, all those startups, basically we'll create the core startup in our campus, and the second level startup, which is specialized to a specific aspect of packaging or to a specific modality in a drug, they will then get forked based on student interest and entrepreneurial zest and zeal of the student, and based on that they will continue to run. So that's the model we are following. So unless India creates this startup ecosystem in a massive way, India is always going to be a slave country, and it will never emerge as our students will continue to run to the US and all that to seek better labs, better infrastructure, and all of that. It will continue. That slave mindset of the country will continue and perpetuate. And the only way we will get back our people is if Trump kicks them back. We don't want that. We want people to grow, develop this country. So that's the larger picture, and I'll keep on giving you larger picture through this forum. And okay, so now today let's get down to more mundane stuff, which is I'll summarize what we did in the last class. I'll go through the code, and then today we'll have small enhancements to the code, not anything very significant. In fact, those of you who have understood last class code, understanding today's code is going to be a cakewalk. So I'm going to start with the last class code, because we are going to enhance that last class code. That is the mini batch gradient descent. And I will again walk you through some of the salient aspects of the code. As usual, I will start from the maybe the creation of the network. And I keep repeating this because I'm hoping everybody understands it and how that data structure is growing. Because when you come to PyTorch, I'll again use the same situation, but I'll tell you what PyTorch is doing, how the data structure improves with PyTorch. So our concept is layers. Our primary data structure continues to be layers. And in layers, there are neurons. So there is a list of layers. Each layer is a list of neurons. Each neuron is represented as a dictionary. So there is a set of neurons. So they are okay. So this is one element. This is a list of layers. Each layer is a set of neurons. So this is a list of neurons. Each neuron is represented as a dictionary. One of the fields in the dictionary is weights, and the weights itself is a list. And then we have added two more fields to it. One of the field is output of each layer. We have added this. This is a scalar value. This is not a list. Then we have added a delta, which is also a scalar value associated with each neuron. There is a delta. And then we have added a parallel data structure to this, which is the gradients which we accumulate. So the gradients data structure, it could have been added here also with every neuron. Along with the weight, we could have added gradients. You could do that. But the gradient data structure actually mimics the neurons data structure. So it's the gradients are maintained for every layer. So it's maintained for all the list of layers. The list of layers, as you know, consists of neurons, list of neurons, and each neuron. This is every neuron. Each neuron has a weights dictionary listed with all the weight. This list is for all the inputs connected to that neuron. So similarly, here also for every neuron, there is a series of weights. So there is a series of gradients, which is again a list, which mimics this list, right? Which mimics in the sense which is similar to this list. So as many weights, as many gradients, which are accumulated for a batch level, and then it is done. So then they are applied at a batch level. They are not applied after every weight. We watch for the gradients to be accumulated and then applied, so that we don't swing the weights every now and then. The main mean of the gradients are accumulated for every neuron. The gradient is accumulated, and then the gradient, once the gradient is accumulated, we basically take the gradient and add it up for all the samples, and then take an average divided by batch size. So that's how the gradient is done. So is the gradient is maintained for every weight. That's why I've shown it as a list. For every weight, there is a gradient. So in a way, the gradient is maintained for every weight. There has to be a gradient, because the gradient for a given weight is different because of the chain rule, and that is how it is applied. Without this gradient, we won't know the updates to the weights. So gradient is accumulated and then applied. So we are summing over a batch and then applying. So this is what we did in the last class. Okay, if you will. Now I'll first walk you through the code of this session, of this last class. Just quickly, we'll walk through the code. We'll look at the data structure. So there are two things. One is called the zero grad, which is done at the beginning of every batch. We zero out all these gradients, so we make this all zero. Then we have for every sample we have accumulate gradient. Okay, and then we have at the end of the batch we have apply gradient. Okay. That happens at the end of the batch. So once again, before a batch starts, we zero out all the gradients, because the gradients are accumulated only for the batch. The gradients are the things which have to be applied on the weights. We accumulate the gradients after every calculation. We accumulate after every forward propagation. During the backward propagation, we accumulate the gradient, and then once a batch is done, we take the average of the gradients and apply them for weight computation. That's how we do. So that's the data structure, and that's how the process is. So we will go through this process once again. We went through this in the last class, but since most of you are new, I would rather spend time emphasizing this, and then we will actually talk about how this all works and all that. Now, I think what I'm going to focus on is primarily this code, because I'm not going to spend more time talking about forward propagation and backward propagation, because that's essentially the same. Backward propagation has not changed. Backward propagation does what? In one line, the answer is that it works towards back propagating the deltas. Remember, all our gradient computation is based on deltas. So yeah. Okay, somebody had asked a question which I noticed just now. Is that, are all the past 3 classes available on KMIT Vista? Yes, they are all there. You just have to check, sometimes. Okay, so now I'm going to talk about these 3 algorithms, these 3 functions: zero grad, accumulate grad, and apply grads. I'm going to show that, because the rest of the code has continued to remain the same, I think, for the last 3 or 4 weeks. So I will not again talk about it, but let's focus on the essentials of this, understand this. And as I was mentioning, this delta is the key which gets propagated backward. Okay. Now, before I start, I think I will mention a little bit about this delta back propagation, because I have found that students find it a little difficult to get this delta at the first go, and so delta depends on error and all of that. So let's look at some of the code which does this delta calculation, and then we will do zero grad, accumulate grad, apply grad, and after that I will this is actually a repetition which I'm going to do again, and then I'm going to show you how to do the basically learning rate decay and the momentum. So let's briefly, if you're clear about these data structures, I think we can walk through the delta code a bit. and get a hang of that, and then let's see whether you get that. Okay. So here is where the deltas are computed. This code is the code for back propagation. So let's look at, since all the code is available on the screen at this stage, let's quickly go through the code and understand how back propagation works. I hope you'll get the idea of how back propagation works clearly if you have not got it already. Okay. First rule of back propagation is it starts from the end. Okay, because it's for I in reverse range length of network. Network is a set of layers. Remember, is a list of layers. So we are starting from the last layer. That is, we are starting from output, then going towards hidden, because we are having only one hidden layer, and then going towards input. That's how we are going. So there are only two layers in the network: hidden layer and output layer. So, but doesn't matter how many layers are. Hidden layers can be any number. In fact, in real life, as I told you before, there could be thousands of hidden layers, and each hidden layer could have thousands of neurons. So that's okay. So we start with a particular layer. A layer is equal to network I. We work with a particular layer. So we start with the last layer first time. We make the errors list empty in the beginning of the loop as we work with every layer. So in one iteration, only one layer is processed for backward propagation. So if I not equal to length of network minus 1, no, don't look at this first, because I is not equal to length network minus 1. We are starting with the last layer, so we will always start with the else first, because this will be it's starting in the reverse order, and I will be initially equal to the length of network minus 1, because it is starting from reversed range length of network. So it will start from the last value minus 1. That's how Python works. So we will come here else. Now we are going through all the neurons in the layer. This is just enumeration, so it just gives the index of the layer in the thing, and for each it gives the index of the neuron in the layer, because we are enumerating the layer. Layer itself is a list. As you know, when you say network I, we get the list. So we go through each neuron of the output layer. For the output layer, the error is very easy to compute. It is errors dot append neuron output, whatever is the output, minus expected j. So this is the error. This is for the last layer. That is the error. Okay. And okay, then for every layer, we also use a term which is the derivative, because see, this term by itself doesn't carry much meaning. This is just giving the derivative of the error. Now, in order to back propagate it, we just don't need the derivative of the error. See, this is nothing but the derivative of the error. You know how this is called derivative of the error? You remember 1 by 2. We had O1 minus E1 the whole squared, or rather it was E1 minus O1 the whole squared. This was the error, and this is the first derivative of the error. If you take the derivative and reverse the sign, this alone will give the first derivative of the error. But that is not enough, because this O1 has come. If you have to take it back, you know, we have to take it back through the derivative, because you remember the dou L by dou W, even for the outer layer, you will have to take the transfer derivative. That is, we'll have to take the derivative of the activation function and multiply it with the error to carry this error backward, because of the equations that we had worked out in so many sessions earlier. So, so this is basically, you know this. This is O1, 1 minus O1, right? Sorry, is it O1 minus 1 or 1 minus O1? Sometimes I forget. Okay, O1, 1 minus O1, yeah. So this is the derivative. So this is what we were working with. So that was the derivative. and that's why we are computing delta not just as error, but error into O1 minus, because we want the dl by dw. Remember, we want the dl by dw, and therefore we want it to be passed to the derivative. That's one part. That also will not give you the dl by dw. That will give you dl by, see this, the derivative of the loss with respect to dO1 and remember there is that dou Z1. So this will give you the dou O1 by dou Z1, but we still need the dou Z1 by dou W1, which we will get because of the other part. Okay, but this basically will give you this much part. This will still not give you dou L by dou W. For that, we need to do something else on the delta. But this captures the delta. So this is the delta. This captures the delta. Okay, for the outer layer, that is how the delta will be. Okay, so dou L by dou O1 is just O1, and this is O1 minus E1, that is. And this is O1 into 1 minus O1. So this is what we have got. This is the transfer derivative, and this is what we call delta. Yeah. It still needs to be multiplied by the input to this layer to get the actual dou L by dou W, which is needed. But we don't do that. We don't store that in delta. So this is how the delta is computed. Now, for the other layers, if you recollect, we have a different way of computing delta. For each neuron of the earlier layers, we look at the neuron of the outer next layer and pass on the delta back using this equation. So I think this is understood. This part is understood. I have explained this before also. I'm just mentioning this again. We have explained this again. See, this is the weighted delta, which kind of goes back, right? The intuition here is, let me just rub this and give you the intuition behind this. Again, I'm doing this again and again for the same reason. I think I'm repeating this for the 4th or 5th time. Okay. So for the hidden layer, for example, or any hidden layer, where this is the neuron and this is the layer. So here, this is the outer layer. This is the hidden layer. And we have computed, let's say, the delta here. So this is the D1 and this is D2. That is what gets computed first. And how does that delta get passed on here? Now there is a weight connecting here, this input and this input. So this is the weights connecting. Let's assume that the weights here are W1, W2, just some weights. So how much of that delta comes here? D1 into W1. Delta times W1 is what comes here, plus. So it is sigma D1 DI WI, which kind of comes here. Okay, this is the delta for this guy, and that is what is getting computed here. So if you look at this, you see this. You have to be able to understand this and watch this. Now we are going through the earlier layers. How do you compute the delta for that? The delta is for the earlier layers. We go through all the neurons of this layer. This is J range length of layer. That is, we go each neuron. For each neuron, we compute the error by taking that delta and bringing it back. For computing delta, we also need to do the transfer derivative thing. So this is actually the error. What I just said is the error. Error is equal to this. So this is how the error is passed back. For each neuron in network I plus 1, I take error plus equal to neuron weight J. That is, I take that neuron weight J into neuron delta. Now, from where did I get the neuron delta? I looked at the neuron of the next layer. That is, I computed the neuron of the next layer, and the weights are also available there. Weights of this neuron here are available with weights of this input here are available with this neuron, and they are available with this neuron. All the weights connecting to this neuron are available there. So we are going through the weights for the jth neuron of this layer. For each neuron in this layer, we are going through neuron weights j. That is, we are going to each neuron of that layer, of this layer, and see, we have to go through every neuron of this layer, take the delta there and pass it back, and that becomes the error here. And this is for the neuron of this layer. For this neuron, the delta is, look at the neurons here, multiply them with the deltas and the weights, and you get the error here. So this is what we did. Remember, this is only computing the deltas, and then we have to compute it with the transfer derivative of the output, because here also there is an activation function. This doesn't go directly here, right? There is an activation function, so this takes care of the activation function also. So then the delta comes. So the delta is first the error, and then the transfer derivative of the output, which is always O1 1 minus O1, because whatever we, in this case, what is the output? H1 1 minus H1. That will be the thing. Depending on what the layer you are talking about, the output will change, but the transfer derivative will remain the same. So that's how this thing will get computed. I think once the deltas are computed, once the deltas are multiplied by the input for that particular layer, we get the actual dou L by dou W, and we can then use it in our weight updation. Okay, so this is what the classic back propagation is. Guys, this is the most important part, how the deltas get propagated back in form of errors, and then the delta computation by applying the sigmoid, because we have to get dou L by we are actually getting dou L by dou Z1, which is the output dou L by dou O1 and dou O1 by dou Z1, or whatever is the Z there. So this is what we are getting, and this is what we are taking it back and doing it. Once we get this, then we multiply it by the input, because Z is Wi xi sigma. So if you take the derivative of dou Z by dou W, it will be only the input which remains, right? So that's why once the deltas are done, we are actually kind of done when it comes to application of the weights, okay? Application of the correction or the change. So once we are clear about this, actually we are basically understood this. You know, what I have seen in practice is most people don't get this, how the deltas here are used to compute the error here, and you know, they just don't get it at that particular point. And then once they don't get it, basically they don't understand how backpropagation works. They don't understand then how fine-tuning works, how to freeze layers. Everything becomes you know, kind of a kind of a khichdi in their mind, and then we pay the cost. Okay, so this is what you should get. Okay, now this, how the application of Mike. Somebody's transcribing. Fine.
Yeah,
That was the last message. I saw that. That's good. Great, guys. If you are using any tool to transcribe, it's good. Many people do this, and actually, yeah, Gemini also gives a transcription facility. You can use external transcription also, by all means. In fact, you know, maybe one day I'll talk to you about the initiative which I think I mentioned last time, called GOGTE, which does something very interesting based on this. But anyway, not now. Let's finish the back propagations well. Okay, so this is what I explained just now. Now we are going to look at the application of this. Basically, how the back propagation gets called in the training loop in the original stochastic gradient. And then we will see what changes we did in the last class. And then we will talk about what changes we did, we are going to do today. So we will, no, first let's look at the original training network. No, this is not the original. The first code. Then we'll look at this code without the accumulation of gradients, without doing mini batch. Yeah, this was the original code of training. I'll just quickly go through it. I think we should have that. So this was our original training with the stochastic gradient. That is, with every sample, it was doing the training. I hope you're aware of this. For each epoch in the range, for each row, for each row in the training data set, training is a data set, so we go through each row. We say pick up the input is equal to row minus 1. That is, we ignore the output. The last column in the input is the output. So we ignore that. We don't want that. So we take inputs only up to everything except the last value. That is the first time. Then we forward propagate using that input. Then expected, we make it 0 initially. And then we say the expected value int row minus 1, we fit it in the output. So that particular value, because it's a binary output, so if there are two outputs, we make one of the values 1, the other value remains 0 if this is one of the output. The other output for this example is this or this. So if there are two outputs, or any one of the, if there are more, then any one of the output can become 1. Only one of them will remain 1. So that will remain 1. Then we accumulate the error, the total error, that is sum expected across all the outputs. We accumulate the error, which is sigma EI minus OI the whole squared for all the outputs. And then, this is important, then we backward propagate the error, what you just saw. And after that, you update weights after every change. We'll go to this update weights in a moment, but we update the weights every time. So for every row, the weight gets updated. So that is called the stochastic gradient descent. And we talked about in the last class, if you keep updating weights after every sample, it is like shifting with every sample, and that gives a very wayward way of updating weights, does not stabilize the weights faster, and does not stabilize the change faster. So that's why we don't do this. This is not a good thing. Of course, for the first time, we did it that way. So we said, this is not the way we should do. We should backward propagate. After that, what we should do, as the weights, as the deltas are backward propagated, what we should do is, for this sample, we should not do this. We should not update the weights. Instead, we should accumulate the gradient. Okay. After every sample, we should accumulate the gradient. And before every batch, so we will do this in batch, we should do a 0 gradient. And after the batch is over, we should say apply gradient. I am going to repeat this, and then we are going to see how these changes are made to the original code. The back propagation code is not changed, by the way. Only the training code is changed from this example to the next. And so the first example, we had updating happening like this. With every sample, the weight was getting updated, leading to instability, leading to I see one weight, I change. Again, I say something else, I change. So the outliers, that is the strange examples, every sample data will have some strange examples. They were dictating how the change will happen. Okay. So now we are going to do this, and 0 grad before batch. Okay. Before batch starts, accumulate gradient on every sample. Okay, apply gradient after the batch. Okay, so this is the change we will do. So why don't I show you the training loop with mini batch, and then we will talk about how each one of those pieces got implemented, and then we'll come to today's session of how do you make changes. Okay, so now I'm going to show you the code which we saw last class, and hope that it is very familiar. The way we generated this code, we didn't write it. We asked ChatGPT to give us a code with mini batch and then all the other changes. Let's look at this code and try and get the difference between this code and the previous code. There is some new things which are not necessarily there, but since they are there, I might as well explain them. This is what it is. This is the training network using mini batch. Now, one parameter which got added here is the batch size, okay, which is a new parameter to the function. For epoch and range, so we go epoch by epoch. In the beginning of the epoch, we make some error 0, obviously. We take data is equal to list of train. This is our training data. And this is an important step where we do shuffle of the data every epoch. This shuffling is done. It just randomly rearranges the data for every epoch. Epoch is broken into batches. Epoch means one traversal of the entire set of data. Every time I shuffle data. Now, why do I shuffle data? Quite often what happens is when the data is generated, it is generated in a particular order. And what happens is data which is similar gets aligned together in the data generation. That is, during data generation, there is a possibility or there is a risk that the data, similar data gets aligned together. That is, the similar samples get aligned because somebody may have done some sort or something. We have all kinds of people who like sorting data when it comes from the data frame and all that. Actually, we don't want data to be sorted. Why do we don't want? We want every batch of data that we see to contain samples which are a variety of samples. Because if you get in every batch a variety of samples, then we have seen all the samples in all various kinds of data in a sample, and then we are averaging. It generally gives us a much better answer and much better learning than first seeing only all data. It's like saying first get all the bright students data and then get all the dull students data, in decreasing order of their intelligence. Now that is not a good way at all. Because I'm not learning anything from this batch. It is the same kind of people, very homogeneous data in a batch. I don't want that kind of data in a batch. I want my batch to be very esoteric, to be very having a variety of data. So I don't want this kind of a thing to happen. And because I don't want this kind of a thing to happen, before I go for batching, I do the entire data to be shuffled. So some kind of a randomization is done to the order of the data. Data doesn't change, but basically the order of the data is disturbed and thrown kind of randomly. That's always a good way of starting our epoch. This is a good technique. So when people see this, I like it. Okay, and shuffling is generally done randomly. Normally, there is a seed which is used to do that so that you and I get the same shuffle. And it's just like shuffling a pack of cards. The card doesn't change, but they're just shuffled together differently. Okay, so that's a good idea to do always. Okay, before a batch starts. Now let's see how the changes are. Then we'll go to the individual pieces of code. Okay, so now a batch has started. Okay, so this is a batch. So how do you make a batch? you always remember an offset called start, and then start to start plus batch size. So basically, you are taking all the data samples in a batch, which are from start to start plus batch size, and then you'll increment your start every time. So that's how you'll proceed. But then the current batch size is length of batch, and then because this is a batch of data, or it could be directly batch size here. Then before the batch starts, you're zeroing out all the gradients associated with all the weights. Zero gradients, which is associated with all the weights. Remember, the gradient data structure is again first layer wise for each network consisting of multiple layers. For each layer, there's a list of neurons, and for each neuron, we maintain the grads, which is maintained as a list of weights. So for each, so this is for the first neuron. These are the collection of weights associated with that. The neurons, the gradients are kept, and so this is a list. Okay, so it's a list of lists. Okay, the gradient data structure is a list of layers. Each layer has a list of neurons. Each neuron has a list of weights. So therefore, it has a list of gradients. Each gradient for one weight. Okay, so that's how the data structure is. But we'll come to that. At the beginning of that, we zero out all the gradients because we want all the gradients to go to zero at the beginning of the batch, and then we'll see what happens in a batch. So I'm going to rub this, scroll down, and check how does each row progress here. Let's look at this part, and then if you understand this, we will understand the individual pieces of code. Okay, so let's watch this. So again, row, this is the familiar. We don't want to look at the output. Then output is equal to forward propagate network input. The expected output is 0 for I. We have seen this already. This is the forward propagation. Expected is whatever. Expected is int row -1 is equal to, that is, we have set that output to 1. We compute the error at the output layer, then we back propagate. This gives us all the deltas. Now we don't do the application of the weight update. So we don't do weight update here, which was there earlier. I hope those of you are paying attention has grasped this point. We are not updating the weights here. If you looked at the earlier algorithm, we were updating the weights here. We are not updating the weights here. We are only accumulating the gradients here. Okay? The gradients are getting accumulated here for the batch, and then so this goes on for every sample in the batch. This for loop is done. Then outside the for loop, we apply the gradients at the end of the batch. So gradients are applied at the end of the batch, as it should be. Okay, so this is what is happening. Okay, now to appreciate this better, we have to see these three pieces of code, which is zero gradients, accumulate gradients, and apply gradients. So I'm going to show you all three, and then hopefully we will move on to the concept which we need to understand. Okay, now we will look at the gradients. So let's scroll up a bit and watch the gradient data structure first. Apply gradients, accumulate gradients, zero gradients. See this gradients. Here is where the gradients are getting done. Now what is getting updated here is grads. Yeah, so you can see here how the data structure is changing. The zeroing of the gradients. Let's just understand how the zeroing of the gradients, which actually creates the gradients. So gradients is a list for a layer in network. There is this layer gradients. So we have the grads list, and then we have layer grads, list, that is, this is the gradients of a particular layer. For each neuron in that layer, uh, for each neuron in that layer, each neuron, remember, in that layer will have weights. So instead of weights, what are we doing? For each neuron in the layer, which itself is a list, we are creating layers.grads append. So we are appending a list to layer grads for each one. So this is the weights associated with all the weights of that particular neuron. This is all 0. Okay? So these are all 0, comma 0, comma 0. So this is the gradients. This is the layer grad, and this is okay. This is individual gradients. Let me see. This is the layer gradients. Each layer has many neurons. Each neuron has many weights coming to it. Each of the weights has gradients, and therefore there is also the grads. Okay. This data structure has to be understood. So once again, the grads data structure or the gradients data structure is a list of layers, and then each layer has a list of neurons. Each neuron is connected with many weights to its inputs. So for each of the weights, it keeps a gradient which are connected to that neuron. It is the weight which is connecting inputs of that layer to this neuron, and that is the individual things. For each one of them, initially the gradient is 0. Okay, so this is the 0 grads code, which is done when, which is done at the beginning of every batch. I will zero out the gradients, and that's it. So for every batch, what will I do? For every sample, I'll accumulate the gradient. That is, I'll accumulate the derivative, but I'll not apply the derivative. I'll accumulate the gradients for the entire batch. I'll keep adding them up, and then I will take the mean and apply it when I say apply gradient. Okay, now let's see how the accumulate gradient. The last element of the row is bias, isn't it? Rather than output. Oh, sorry. Last element of a row is a bias. Depends on which row you're talking about. When you take the input, the last element is not the bias, it is the output. I think you should ignore the bias for some time. For some cases, the bias is important, but then we will spell it out where it comes. Okay. But for input of row, there will not be any bias in it. Okay. It will be the output expected. Okay. So when you say here, it is not the bias. When you say here, it is the bias. Okay. I'll explain as I go. Okay. Now, how do you accumulate gradients? Okay. Accumulate gradients happens in this way because we have computed. Remember, before we apply gradients, we accumulate gradients. The backward propagation has happened. Okay, what has the backward propagation done? Let's just understand that. What has the backward propagation done is for all the layers in the network, and for each layer, for each neuron in that layer, it has, remember, each neuron has a weights key field in the dictionary. Each neuron has a dictionary, and against the weights, there is this whole series of weights. Sorry, this is the first element of the dictionary. Now, remember what has happened here. It has computed during forward propagation, it has computed the output for every layer, which is a scalar of that neuron. And also it has accumulated the delta. All this has happened in backward propagation, which is also a scalar. So again, these are the layers. These are each neuron in the layers. This is each neuron in the layer, and each neuron is represented in the layers data structure, in the network data structure as a dictionary. Remember? This is each neuron. Each layer is a collection of neuron, and the network itself is a collection of layers. So each neuron has these fields in its dictionary. Weights field, which are the weights associated with that neuron, connecting input to it. Output, which the neuron has produced during forward propagation. Delta, which is the delta which has been computed in a different way for the output layer and for all the hidden layers. By back propagating the delta, this has been computed. So all this is there with us in the network data structure. It has been updated. This is all there for us. Now what we are doing is we are computed all this during backward propagation. Now we are using this to accumulate the grads data structure. We are going to use it to update the grads data structure, which is to give you a mimic. Grads also is a list of layers. Each layer has a list of neurons. Okay, this is a list of neurons. Each neuron has a list of gradients. This is how the grads data structure is kept. It's a list of lists of lists. It doesn't have a dictionary. Okay, so that is how it is kept. Now this has to be updated based on this. Let me change the color to spoil the monotony. Yeah. So this is how this is going to be updated. Using this has to be updated, and the gradients have to be not yet applied, but they have to be computed and accumulated after every batch, after every sample, and they will be applied after every batch and then zeroed out. So after every back propagation, we will take this data structure and update these weights. Now let's see how it does. So now we are looking at a row here, row inputs. So we need the inputs. Row is this for I equal to 0, else neuron output for neuron in. What this means is for the input layer, I take the actual for the input. For the first layer, I take the actual input. For all other layers, else if I equal to 0, else if I is not 0, that is all other layers, including the hidden layer and the output layer, the network output of the previous layer. See this is for I in network I minus 1. The network output of the previous layer is taken as the neuron output. Okay. So please understand how the inputs are computed for all the. This is finally the input for each layer. For the inner layer, the input is actually given from row, and for all subsequent layers, the input is the output of the previous layer. I think that at least you should grasp looking at this intuitively. This is network I minus 1. Okay, I have obliterated that a bit, but this is network I minus 1. So it is taking the output of the previous layer as the input for the next layer. Okay, so we have the input with us for every layer, for every neuron. We know the input that is going to come useful, because when we compute the gradient, delta alone is not enough. The delta has to be multiplied by the input to actually compute the gradient, which has to be applied. So layer is equal to network I, layer grads. The same way we are proceeding. We are getting the layer, which is this layer, each layer. See this. This is each layer. This is one layer, remember? And each layer here consists of a set of neurons. Here, each layer also consists of a set of neurons, but for each neuron, this is the layer. These are the neurons. For each neuron, we have a list of weights associated with that neuron connecting the input to this. So you have to keep this in mind. And now, so these are the two data structures. Using this, I'm going to update this for each neuron. Forget this NIDX, just to keep the index so that it becomes easier to refer. For each neuron in the layer, that is, we are looking at each neuron in the layer here, wherever. So first we start from here. So each neuron in this layer, that is, now think of this data structure where we already computed the deltas. So layer grads I, layer for each neuron, for each weight. Now look at it. We have to look at all the weights because that many I have to look at that many inputs, because that tells me how many weights are there in that layer. The number of weights in a neuron will depend on the number of inputs which are connected to it, right? So for J in range length inputs, so that means I'm going, J refers to each weight of that associated with that neuron. Okay, so we are going to every neuron, we are looking at each weight in that neuron. Now using that combination of that as an index in the GRADS data structure. So now we are here, so we are going one level down. So n index, so we are reaching this. N index will tell us which neuron we are talking about. J will tell us which weight we are talking about in this. So this takes us to this neuron. This takes us to the actual weight, which weight we are talking about. This is the double indexing which you see here. So we are accumulating the gradient. How are we accumulating the gradient? We are taking the delta and multiplying it by that neuron's input. So this is the neuron's input, which is connecting an input to that layer. So see, the inputs are coming in this way. So if you connect the delta of a particular neuron with its input, this is the input. If you multiply this delta with the input, you know what is the gradient which has to be applied. Remember, this is because of the equation that I need to do dou L by dou W1, which is dou L by dou O1, dou O1 by dou Z1. This is captured in the delta. And then I have dou Z1 by dou W1, which is, if you take Z1 as Wi xi whole sigma, becomes, if you take the derivative of this with respect to the actual weight, is equal to the input. So input of that layer, that is why this input comes. So then only you will get the dou L by dou W1. I hope the real essence is you understand this, you understood AI. Many people, why many? Most people I know just don't get this correlation between this and this. And that's why I am struggling with you guys since 2-3 weeks to give you this insight that delta gets you this. This is delta. This dou Z1 by dou W1 is equal to input. And how did it come? Intuitively, you understand that if I take Wi xi and take the derivative of this with respect to W, it will be xi, the input. So that is why this input is this. Okay, so this multiplied by delta will give me actually dou L by dou W1, which is what is the gradient, which I need to multiply it by the learning rate or whatever and apply it. So the endeavor is to compute this layer delta. And for the last layer, for the last bias term, I just take it as the neuron delta, whatever. I think you ignore this for the time being. It does not matter to your understanding. It's very simple. It's basically, we are adding one more neuron kind of thing, which is instead of J, we are using neuron, which basically it's not a neuron. It's there everywhere. For every weight, this is the weight. The weight index is not there. It's only for every neuron there is a bias value. So that is the bias value. Okay, so we are adding that. That is exactly equal to neuron delta. Why? Because see, if you take the derivative of this plus B, which is what Z is, if you take the derivative with respect to B, it becomes just 1. Okay, so it's just the neuron delta. The derivative is only 1 because dou Z1 by dou B will be equal to 1. So that's why we just take the derivative. We just take the delta. There is nothing multiplying this. Okay, you can see there. This is just the delta. Okay, so this is what is accumulating gradients. We are doing it after every sample. We are taking these weights and transferring it into the gradient. We are just taking the weight and accumulating it into the gradient. Whatever the value is, we are accumulating it into the gradient. This is called accumulate gradients. Okay? This is an important step. Now, this step will change a bit in the next iteration I'm going to show you, but we'll wait for that. Okay, so if this is understood, we are pretty much kind of done. Let's now see what we do at the end of the batch. We apply the gradients, which is pretty simple. We just take this and use it to change the weight, that corresponding weight. It's again playing with the arrays and with the data structures. Now, these data structures will become mighty simple when we use PyTorch. But PyTorch is doing exactly this under the hood. Only thing is, PyTorch will hide all this from you and make you dumb. The smart guys will know exactly what is happening, and therefore they will get that extra loop or extra thought. Okay, so we are now going to apply. We are going to go through. We are going to apply the gradient to every weight. So see the way it goes. It's an iteration of the network. We are going through all the layers of the network. We are going through. We are going through all the layers of the network. We are going through all neurons of all layers of a network. All neurons of a layer. All neurons of a layer. And now what are we doing? We are going through each weight of that neuron. See that for each neuron there are weights, so we are going through each weight in the neuron. Each weight of the neuron, and we know now what to do. We have already computed the gradient. What we are doing for each weight is we are taking all the accumulated gradients. See, this will be the layer, this will be the neuron, this will be the weight. You see the three indexes here. I told you gradient is a list of lists. This is the layer. I is the layer. N index is the neuron index, and J is that particular weight of that neuron. Particular weight of the neuron. The jth weight of the neuron is now, whatever the gradient has been accumulated is now being averaged. This is the averaging which is happening. We are dividing it by the batch size because we have been accumulating this for an entire batch. And at the end of that batch, we are applying these gradients. And then we have computed the gradient. And then the new weight of that neuron is changing to neuron weights J. Okay. The jth weight of that neuron, because remember, this is a dictionary. Weight of that neuron is equal to whatever it was minus learning rate times the gradient which has been computed for that particular weight. So this is what is happening. Okay. Now we are going to pause here, and now we are going to move to the next step. If you understood this far, I'll tell you, you have understood almost all of it. And because you'll see the things I had to talk about are very small extensions to this idea. There won't be much fundamental change to the code. It is just the way the gradient is applied which will change, and I'll give the argument behind that, and we will see now whether today's, so far the last 1.5 hours has been productive or not, and then we'll come to today. This is almost a repeat of what we did the previous session. I don't mind repeating. The purpose is you should understand. Okay, so far so good. Fantastic. If you're going to have even 50 such people who have understood this, I will have at least 5 startups coming from this group. Okay, I think we are ready to move. I think now we are not seeing too many people answering votes. Okay, so now I will take you to the next stage, which is we'll talk about momentum. What is the importance of momentum and how do you incorporate momentum in this algorithm? Okay, so here we go. We will now incorporate the concept of momentum in our gradient descent. I'll first talk about the concept, then we'll look at the code. Now on the net, you will see several people, they keep on talking for concept. There was one popular author, popular person with a lot of following actually. who goes on talking about these intuition behind all these uh, momentum and all that, and never shows code which has like some kind of an algorithm without focusing on any data structure, any impact. So guys, please don't look at such videos, because those videos have very little value, and they don't get you anything other than making you a superficial AI engineer. Okay, a true AI engineer's first ritual is understanding backpropagation intimately. Deep learning AI. Anybody who makes life easy for you is doing gross disservice as far as your future is concerned. That's why these series of lectures where we need to go to the depth. Okay, now we talk about the idea behind momentum. The idea behind momentum is very simple. Okay, and this is an idea which is pretty easy to understand and all that. Now, we are talking about gradient descent. Now, the two words gradient and descent is always to be seen in correlation with the loss on the y-axis and the weight on the x-axis. And any and everybody will talk about this convex curve is what we want to go with. So if you're here, this is where we want to reach, right? This is the point where we want to reach, because at this point, the loss is the lowest. We want to arrive at this weight. Remember, all algorithms start with random weights. So, and they want to keep on updating those weights such that somehow I come to this point. And once I arrive to this point, I have got my thing. And it's all about the journey. So far what we have learned is, if you, I just change again the color to break the monotony. We said if my initial loss is here, which is high, then I mean it means that I am on my loss is positive. The curve of the loss curve is positive. Then I have to go down, so I have to apply negative update to the weight. Here I might have to apply a positive update to the weight. So because I'm on the lower side, I'm on the descending side. So I have to somehow descend, whether I go from here or I have to go from here. I have to, if I'm on a lower weight randomly, or if I'm at a higher weight randomly, I have to, in both these cases, descend towards this valley of the lowest weight possible. Now, almost everybody who teaches AI and deep learning will talk about it, and they are right. This is the best way to talk about loss, weight, and the descent which you have to take to this point. And the gradient descent basically describes the process of going from here to here. Now, we talked about what happened if we jumped with every sample. We changed our direction, our weights, that is our weight shifted like this. It would be too zigzag. I mean, it would be too much of a zigzag. That's why we don't do that. That's why we moved in batches, so that our zigzagging becomes more smooth. Okay, but really, and I would also take you to that intuition. So that was correct. That is better to look at a batch of values and then descend, so that our descent is more smooth rather than very rapid and very zigzag. Look at a bunch of samples. Okay. Now, that is very correct. And that intuition, if you have settled with you, it's very nice that that intuition has been obtained. Now, talking about the descent further, okay, the question is, when you are descending at this point, okay, just think about this point. Okay, just take one point and think about this point. When you are descending at this point, okay, how should you descend? Okay, just philosophically. Okay, now my descent at this point, descent means the step that I take so basically I have to decide how much, by how much my weight should change. Weight or weights should change. This is by how much, quantum of weight change. Now, the quantum of weight change, the way it should be decided, is it the current batch alone which should influence the weight change, or the weight change that I do should be influenced by this batch for sure, the current batch that I have processed. But whatever has been the weight or the gradient of the slope that I have descended with, that is, whatever has happened with the past batches also have gone into the where I am at this stage. So I am here, let's say, this is my weight at this stage. So when I'm doing it, should I only be influenced by this batch which I am seeing right now, or my history, my previous batch, whatever I have observed, previous batches which I have observed, and the gradients that I have observed with the previous batches. Each batch has an accumulated gradient or a mean gradient, whatever, whichever way you want to look at it. The gradients of my past batches, should they influence me or should they not influence me? So should I be only controlled by the current batch, or should my batches of the past be allowed to influence what change in the gradient I will do? Okay, now this is philosophical. It's like saying, I wrote an exam, okay, and the marks that I get, I got certain marks. Now the grade that I get or the evaluation I get, should it be only by the marks that I got in this particular exam, let's say the annual exam, or let's say the half-yearly exam, or should it be the marks I got in half-yearly exam given a certain weightage plus a certain amount of weightage given to my monthly exams should be what I have performed at the end of half-yearly? I'll say it again. See, when somebody says my half-yearly performance, or somebody wants to quantify my half-yearly performance, should it be merely based on the half-yearly exam which I wrote just now, or it should be based to a large factor on the last exam, that is just the concluded half-yearly exam that I wrote? Besides that, I have monthly exams. So should my monthly exams also be allowed to influence my half-yearly evaluation? In essence, that is what we are talking about. It's a very simple idea. People spend 2 hours talking about it. It's rubbish. So the bottom line is, the gradient change that I must apply now should be not just determined by the current batch, but also by the previous batches. They should also influence my gradient, my weight change at this stage. It should not be only the current batch. It should, to what extent my past is dependent and what extent my last current evaluation is dependent, that can be hyperparameterized. That means somebody can set that as a parameter, but I should have the freedom to consider my past also, not just by influence the current batch. It should not be. So I should basically carry the weight. So the current weight update I should do should depend on not just the weight update as dictated by this batch, the batch that I just finished watching, but also to a large extent dictated by the weights that have been observed, or the gradients that have been observed in the past. So that is how it is called. And to give a word to the previous exams, they are called momentum. So this past represents in any way the momentum. This is called the momentum. How much weightage I give to the momentum and how much I give weightage to the current batch depends on a hyperparameter. Normally it's called beta. It doesn't matter whether they call it alpha, beta, or whatever they call it. A parameter decides how much I should have this and how much I should have this. So it's like sometimes they do beta, 1 minus beta, that kind of thing. How beta decides how much of the momentum, 1 minus beta decides what of the next, or they work with two other numbers. They use one number here, whatever. It depends. I mean, that's only incidental to the whole problem. So the essence is this. So basically, if your algorithm can make provisions to capture the momentum of the past, then I think that is what is called mini batch gradient descent with momentum. The equation changes only a little bit. We after every batch, what we do is we have some way of accumulating this momentum. We keep this momentum as something. Now there is a word given to this momentum, this part. We capture it using a word called velocity. Okay. So the past velocity and the current velocity is together what dictates this, because mass being constant. So this is the past velocity, this is the present velocity. So somehow we take both of them into consideration and determine the new velocity. So that's how we do it. And we will talk about the equations, but I'm hoping you have understood the basic truth. Now there is nothing more deeper than that. We will talk about the way it is done. I'll first walk you through the small PDF. We have that PDF, no? We'll walk you through a PDF for momentum. You made that, no?
Yeah.
And then we will talk about the code change that we are doing. Okay. First, I'll show you a PDF which gives a description of how momentum works, and then we will talk about how the code is to be altered. You must understand the code. Any idiot can understand the PDF. Okay. So okay. And momentum. Okay. Now this implementation, I think we'll send you this document. It is not important. What it is basically you implementing an XOR gate using a AI network, but that is besides the point. It can implement anything. So what this does is in the past, okay, this summarizes what we have done so far. This is the pen. Or already we are in a pen. No, we have to do open board and do it. Huh? Just a minute. Huh?
Yes, sir. Right.
Yeah. Okay. So so far what we have discussed, this gives a summary. We have discussed SGD, which is update weights after every sample. Then update weight after a small batch of sample, which is called the mini batch. Okay, this is what we have done. Now you understand how momentum works. Momentum means giving importance to the previous updates also, not just getting influenced by this. So let's see the equations for that. Okay, I think this we can ignore. The network arc is just some data and all that. Yeah. No. Okay, this is where the essence comes. You understand this? We are done. No. Yeah. So I'll drop this. Okay, now get a hang. So forward pass accumulates all the outputs. We know that already. Backward pass accumulates the deltas, and also now we have said how to accumulate the gradients in a buffer after every sample. So after every sample, we know what are the gradients to be applied. We have not applied. We have only accumulated the gradients. After the batch, Now, what we did in the mini batch gradient descent, we just took the average of the weights and applied the average of the gradients. We took the all the accumulated gradients, divided it by the batch size, and applied it. Now here we do it a little differently. We use a term which initially may seem strange. The thing is, this is also called momentum. Okay, they call it velocity, but you can understand this as momentum also. So, okay, let's use the word velocity in place of momentum, in this case synonymously. So here GIJ decides the current batch update. It decides the current batch update. This is what we have seen. This is the accumulated batch update, which is divided. So it's the sigma of all the gradients 1 by batch size. Okay, this is what this is, GIJ. Okay, normally our weight change, which we normally use the equation is, there is no momentum. So Vij is equal to 0. So if you take these equations, I am sure you know that much maths. If you make Vij equal to 0, that is, or you make mu equal to 0, it really doesn't matter. So you make mu equal to 0, that means you have no momentum. Okay. So if mu is 0, then our equations are exactly what you are using. So this becomes, imagine mu is 0, so Vij is equal to minus neta or nu into Gij, which is the average gradient, which has been averaged over the batch, and that you apply to the weight change, mu times the gradient is, that is mu times dou L by dou W1 average over a batch. That you take and you apply, and that is how you get your new weights if mu is 0. So mu is equal to 0 means I'm not remembering anything of my past. Okay, now instead you say I want to remember the past. How much of that past you want to remember is decided by this mu. Okay, so this mu decides how much of my past I am remembering. Okay, so mu is 0.9. This means my current batch does not influence my weight update as much as my previous batch updates, because remember they are accumulated and kept. So my current batch update, if I have a high mu, my current batch update is not as influential to my overall weight update as my past. My past has more impact. If I make mu as 0.01, let's say, that means I'm not giving too much importance to my past. I am entirely dictated by the current batch update. Okay, so I am influenced by the current batch more. Now, how much mu to use is a configurable. In a training, you can configure this mu, and basically, you can decide that I want a particular mu, see how the training is happening, whether the training is happening properly or not. If it is not happening properly, you can change the mu to something else, play around with this mu. That is why this mu is called a tunable parameter of your training, also called a hyperparameter. Okay, this mu and nu, I'm calling it nu, because when I went to school, they used to call this nu. Its names have changed. Nu, I'm just joking. Okay, I call it nu. This is called learning rate. We know this. So this learning rate and this hyperparameter which decides the momentum, importance to the, this is also a hyperparameter. This is a hyperparameter, this is a hyperparameter. These are hyperparameters which are like tuning knobs on your training. So you can decide from one training loop to another training loop, what your mu and how your nu can be or eta can be. So that's how this gets decided. These are called hyperparameters. And these other things, the weights themselves are called parameters. Okay. And so I hope this is making sense to you. This is deciding how much of the past do you want to remember. If you have a high value here, you are remembering a lot of the past updates. If you have a lower value, it means you're forgetting the past and just going by the current value. That is because this is getting added and applied to the weight, or basically this is influencing the weight update. So this, people call it momentum, some people call it velocity, call it whatever you want. Okay. So this is what is the abiding equation. Okay. So it goes on with the gradient descent calculation, what we have calculated earlier, decides on mu, computes a velocity. This is kept for every weight. So this data structure, velocity data structure, will mimic the gradient data structure. So hopefully it will be a list of lists of lists for every weight. We'll maintain a different momentum and a different velocity, because dou L by dou W1 is different for by nature for every weight. Because when you show you the graph, I'm talking about each one particular weight, that graph which I showed you, right? That graph of this. This is with respect to a particular weight, one particular weight. So these are all related to that particular weight. So there will be as many momentums as there are weights. So this is as many momentums as there are gradients also. Gradients are also kept per weight. Now this is a very important intuition, which most of that people who talk on a network bullshit for hours don't give you, that it's specific to a weight. These are real crucial insights when they connect with actual data structures. Okay. So yeah. So this is what it is. So now thinking back, thinking forward rather, initially what is memory? Zero. Initially there is no momentum. It starts with zero. Okay, like a gradient starts with zero, even this starts zero. So this is remembered for the whole epoch. It gets reset only at the beginning of the epoch. Because it doesn't get reset obviously after every batch, unlike zero grades which are done after every batch. Zero momentum or zero velocity is done once at the beginning of the epoch, and it gets accumulated one by one, because it has to remember from batch to batch. This is per batch, and this is across all batches in an epoch. Okay, so you will have to make some small changes to the code to incorporate it. Now, okay, now let's see where all do you have to make changes. Let's listen to people. Okay, no, don't show the change yet. Let me rub this. Let's ask a bit. Okay, let's ask on a chat. Let's see if we have any smart guys. Okay, now can you tell me, any one or two of you, where should I make the changes in order to incorporate this momentum? Is it a significant change, or is it a small change I have to do? Okay, I'll tell the answer to that. It's a small change. Where do I have to do the change in order to incorporate momentum in our original code, the code with mini batch? Anyone? I hope you got my question, and I hope some of you are listening.
Only one near the accumulation, maybe it's
Good.
What about others?
Should it be done near the accumulation, or should it? Okay, let me ask you this. Okay, good. It should be done only one place, because accumulation is still the same thing as per batch. So we won't want to make the change near accumulation. We will make the change near the learning rate. No, learning rate is not changing in this example. Only the place where we are applying the gradient, we will have to make a small change. That is, while updating the weights or applying the gradient, we'll have to make small change. Please remember, guys, this is where AI and you come together. See, you should have first of all an intuition. For example, when I told you about mini batch, and I told you that there are three things there: zeroing gradients, accumulating gradients, and applying gradients. Now we also we made this algorithmic change that I need to incorporate momentum in my algorithm. So if I have to make momentum available, AI will give you the answer. But intuitively, you should know that if I have to apply momentum, I have to remember batch to batch. So obviously, I have to do it when the batch is being applied, where the gradients are being applied. And of course, I will have to make that zero momentum or zero velocity somewhere in the beginning, at the beginning of the epoch. So that is what is called intuition in today's world, that you should develop that insight and that intuition of to think in an AI manner, in an algorithmic manner. That is very important. Code AI is generating fast, but where humans come in is for that intuitive sense and that insight. If you don't have insight, believe me, you'll be replaced. Because if a person comes without insight, if it's just a hollow code creator, code can be created by the machine. In today's world, all code will get created by the machine. What you will retain is your insights about a particular domain, about a particular problem, about a particular algorithm. Those insights are very valuable. And if you are able to build a collection or a library of such insights, or your mind is oriented towards learning the insight or absorbing the insight, then you will have a great future. Otherwise, I don't know. Okay. Otherwise, whatever Jeffrey Hinton, the godfather of AI, is saying is true, that we will all become jobless wonders, because a human being without insight is going to be automated. Okay. The only thing AI can't automate is insight. Okay. One of the insight here is, where do you make the change? AI will do it, but you need to get that feeling. Oh, this is where I would make the change. Okay. Now let's look at the modified code with the weight update, with the momentum update, and see how it's incorporated. Okay. So let's look at the code change which we have done. So now we'll look at the code. We understood what we have to do. Okay. So let's look at the momentum code. I think the rest of the code we can ignore. Okay. Let's just highlight the changes which we are doing. This code generated by ChatGPT. So I am not going to claim any great thing about it. Okay. Okay. This is the data structure which we have. Code good. This is just send it in different way. This is all same. Activation. Let's just keep going. Forward propagation will also remain the same. Backward propagation will also remain kind of same. Yeah. So zero gradients will also remain the same. Yeah. Accumulate gradients will also remain the same. No change. Now, two things: momentum initialization and update. So initialize momentum. It's very simple data structure. You see there on the thing. Look at this. Define init. This is just creating like init grads, like grads. This is creating that data structure. So I am sure you understand init momentum. So we have to create that velocity data structure. So with each neuron, so you know what that data structure is: layer, neurons in a layer. With each neuron, we have a series of weights. With each weight, we have a gradient, and with each weight, we shall now have also velocity. This is on a oh, they are adding it not separately. They are adding it in the neuron velocity. They are adding one more. Okay. So okay, let me take this back. That they are adding it in the not as a separate data structure, but they are expanding the layer data structure, the original layer data structure. So I'll just make the change and tell you what has happened because of this. Layers, neurons in a layer. Each neuron is a dictionary, has weights, which is a list, then has output, which is a scalar, has delta, which is also a scalar, and then it has this velocity for every weight, which is a vector, mirroring the weights. See this neuron velocity is this. So it's maintaining it and it's zeroing it in the beginning. So it is maintaining it in the data structure. Actually, you could have maintained the gradients also here. Okay, we will not worry about it. So this is the data structure. So layers, neurons in each layer, each neuron, the weights connected to it, the output of that neuron, the delta which is applied to the neuron, and the velocity for each weight. There has to be a separate velocity because each weight will have a different momentum. Each weight will descend in its own different way. Okay, so this is what this means. So it is, they have recorded it here. Okay, now in place of apply gradients, it has changed to apply gradients momentum. Okay, and this is the momentum, which is the, I think this is the beta, or whatever the weightage, or sorry, mu, whatever the weightage we want to give, that is what it is. This is learning rate, that is new. Batch size is batch size. These are the two hyperparameters. See, both the hyperparameters are passed as parameters to apply gradients momentum. You can get this code I told you by describing what each does and getting the thing. Yeah, I would be happy to lend his services to you. Okay, just a minute. I'm just going to show you the code.
Yes.
Yeah, I think it's fairly easy to understand this code. This is the old update gradient. So we go through each layer in the network. We go through each neuron, each layer, each neuron. Now we go to each weight in that neuron. J is a particular weight or one weight associated with that neuron. We already know how to get the gradient average. This is what is the gradient average. This is the GIJ as they call it for the ith layer, jth neuron, jth weight of a particular neuron. So actually there should be 3 indexes, but that's okay. GIJ, then previous velocity for this weight is this. This is what we have stored earlier for a particular. Go to the velocity, go to the jth velocity because we are looking at the jth weight. So get the jth velocity, old velocity. This is the momentum. This is a stored momentum. Initially, it will be 0. Remember, I just showed you that data structure, neuron velocity J. This is a key field, and J is the jth weight. So the velocity of that jth weight or the momentum associated with that jth weight, initially 0, but subsequently whatever is the past. This is the past velocity or past momentum.
Old one.
Yeah, this is the earlier one. Now the new, this is the new momentum is equal to momentum. Momentum, remember, is that parameter which I talked about, mu, which is passed as a hyperparameter to this thing, mu into Vij. Vij is Vij, which is this velocity, how much importance I am giving to the past. This dictates the importance giving to the past minus learning rate times grad Ij. This is the accumulated average gradient which we had applied. Earlier, we had just applied it directly to the weight. And now we are passing it through the momentum. That is, we are taking the old velocity, multiplying the old velocity by mu, deciding how much of that old do you want to remember. Okay. And then applying the learning rate times the gradient descent. This is the old stuff, learning rate into gradient J. And then neuron velocity J is equal to Vij. This is again, I am remembering whatever I have applied. And I am now applying it to the weights. See, this is the weight getting updated. The same equations which I showed. I don't mind writing it again. Vij is equal to mu times Vij minus n times eta times mu times the gradient the accumulated average gradient. This is into and then wij, the new weight, is equal to wij plus vij. So the vij gets stored and gets updated, and wij again gets updated with this vij plus vij. So that is what this is happening. This is the weight update. This is the only change, that is to update, apply gradients. So now earlier I was blindly applying this gradient to this weight. Okay, this was this earlier weight minus n times the accumulated gradient, average accumulated gradient. Now I'm introducing this past term. This is a good way to remember the past, because initially it will be 0 and this value will accumulate. It will take into consideration the past history and the current gradient with certain values, and then it will do this. This you can say 1 minus beta times that. There are many ways of doing it. Those are just linear changes to this equation, and they are not important. As long as you absorb this concept, we are kind of understood the issue of momentum or velocity. They call it velocity here. Other than that, there is no change to the whole code. This is the only change we are doing to the whole code, which is we are bringing in past memory of the gradient changes that we have applied. Okay? So this is what is the momentum with mini batch gradient descent. And now, okay, let me again ask the question. Now, the number itself indicates that many people have disappeared, so probably they are not understanding. But again, I think it is so far so good. So I'll ask the question: have you understood momentum mini batch? Okay, we're just asking. Then we'll have just one small concept and we'll conclude. Okay, there are only that many people now waiting. Okay, I think we are not going to get. Let's look at round number 40 votes. It will take us at least. Yeah. Okay. You made my day. So there's okay. So about 80%, about 80% have understood. Remaining people, I think you can listen to this again. I'm sure you'll understand. Important that you understand. Yeah. Okay. So we have moved. Now we are coming to the last stage of our backward propagation story, where we'll talk about learning rate, which we have kept fixed as of now, from sample to batch to batch. We have not changed the learning rate. We have changed the weights, but we have never changed the learning rate. So one minor change we will do is like this, and I'll first give you the intuition behind it. Then I will tell you how to do it in code. Both we have to, because see, one is understanding the intuition, second is understanding the code which gets generated. Code we have not written. Code has come from ChatGPT. We have only explaining the intuition, but we have to connect the intuition to the code. That's crucial. Okay. And I'll tell you this, I have occasion to talk to a lot of you. I talk to so many of our students, especially in the third year and fourth year. More so in the third year and also in the fourth year. Yes, when I talk to a lot of people, I get this impression that some of you, especially the guys who get the big bracket scores, salaries. Even now, there are seniors among you who are getting 40 lakh, 45 lakh plus. Yesterday, only one student from fourth year got into Google with 54 lakh. I see a very notable difference. Some of you, and the guys who make it to the big bracket, have well-developed intuition. I mean, in essence, if your intuition is not well-developed, you won't get a salary more than 6-7 lakhs per annum. I can tell you the difference. Actually, that because I have been talking to students all through so many years, that is my general impression. If you develop your intuition in these next 3-4 years, then your placement is definitely at a different level. And if that intuition is not developed, that is my basic insight and thinking is not well developed, then it's very difficult to get you placed at a higher premium. Because premium people have very advanced intuition, very advanced thought, very clear insights. And that's what they bring to a company. That's what they bring to a conference. That's what they bring to a discussion. They're the way they talk and the way a typical 8 lakh guy talks, there is a marked difference. You can in fact see the difference. Today I have come to a point where if I talk to a person, I can pretty much decide which bracket of salary is going to come into. uh, of course, circumstances are another thing, but by and large, I can generally give a good idea that this person is of what grade and what category, and that decides. And not only I think quite a few of our people who work in the finishing school will automatically tell, looking at that person, the way he speaks, even a simple question, the way a person with insight and done a lot of thinking answers is different. And okay, now let's talk about the intuition behind. We'll briefly talk about the intuition behind learning rate decay. We are going to talk about learning rate decay. Again, my graph remains that sacred graph which everybody talks about: loss and weight. Now, when we take weight, it's not generic weight. It's every particular weight will have influence on the loss separately, and for every weight we have a different convex function, and we have to find this weight. So now that we are in the quest of this weight, we talked about the way we will do. We will first say we descend batch based. We don't descend with every sample. So we are talked that we will descend with at a batch level, not with every sample. Then we'll descend smoothly because we'll be decided by the previous gradient. So we will our our jump will be not random but very smooth, like this. Now the question comes at every time, whenever I'm updating weights, which is by momentum or by whatever. If you see the defining equation, that was old weight. This is new weight. This is old weight minus. This was either computed via Vij or whatever. Uh, I mean, like you can write both the equations. It doesn't matter actually whether you come to this through momentum or you come through this from without momentum. Basically, this let's write both the equations. So Wij dou L by dou W1, that is the gradient. This is the gradient, nu times the gradient, or you can use the Vij new is equal to Vij old plus, no, not plus. I think here we have minus. Sorry, this is mu times Vij old into dou L by dou W1, and then we have Vij new is equal to uh, how much? Sorry, uh, Vij old plus Vij new. Okay, you either do this equation which was earlier, or you do this equation which was with just mini batch. Also, this is accumulated over a batch. This is with momentum. If you look at even both equations, both are linear equations. So basically, there's just an added term of this, but this is there. So now time has come to focus on this learning rate. Should the learning rate always be constant? Should the learning rate be constant across an epoch or across whole training? Learning rate should be constant. Should the learning rate be constant? The argument is, well, the thing is, what they say is, okay, I'll try and give you the standard intuition, standard argument. They say that when you are at a particular weight, which is in the beginning, when you have just started training, okay, so when we just started training, this was my length of my step. See, you will have to understand that the size of the update, that is the quantum of the update, which is being done, is influenced quite a lot by this learning rate. If this is high, then what happens? Then the change applied because of this will be also significant. The impact of the gradient descent, the impact of the gradient descent depends on the nu. If this is high, then this value will have more impact on this. Similarly here also. So this nu or learning rate has impact on the size of the change. See, this is the size of the change. So what they say is, initially the size of the change should be large, but as we come closer to the minima, the size of this should keep dropping. This should be large. As we come close to the minima, the step should become smaller, and the size of this step has been influenced or will be influenced by this eta or nu. Okay, this will have impact on the size of the step. This will have impact. So what the argument is, or what the intuition is, that initially let the nu or learning rate be large, doesn't matter, because we will move in fast steps. But as the epochs continue, after every epoch, not batch, after every epoch, you reduce this learning rate. You reduce this number. So what will happen? The size of the update which is done will diminish, will reduce. If this is small, the impact of the update will be less on the weight. So the steps will reduce. If you reduce the learning rate, if you decay the learning rate after every epoch, then I will ensure that the quantum of updates or the quantum of the update or the impact of the update will reduce on the weight if this number starts shrinking. So you say nu into 1 plus some kind of a decay factor into the epoch number. So as the epochs increase, this value starts reducing. So don't use this learning rate. Use the learning rate original divided by 1 plus decay times. Decay is again a hyperparameter which defines the quantum of the decay into which epoch you're running. So first time epoch is, let's say, 1. So the decay will be, the divisor will be small. So it will be, this decay also is very small, 0.000 something. Okay, this is a decay factor. This is again a hyperparameter. And as epochs increase, the number of epochs increase, this value will increase. When this value increases, obviously, this will reduce. This overall term will reduce. When this reduces, the impact of this on weight automatically will come down, so that the steps will start narrowing. Okay, so this is basically the intuition behind a learning rate decay. So we should decay the learning rate to reduce the size of the step or reduce the impact of the gradient descent, accumulated gradient descent. Epoch after epoch, we should change, not at every batch, but after every epoch. Okay, so there are some messages, huh? No?
Same message.
Oh, same messages. Okay, so is this clear? The concept of learning rate decay, is this settling? That by increasing the decay as epochs increase, we are reducing the learning rate. By reducing the learning rate, we are reducing the impact of the dou L by dou W1, which is the gradient descent, on weight. So the weights will start decreasing or increasing, for that matter, slowly after the initial big steps. Okay, epoch after epoch we should reduce. Now this is a small change. As I said, it is epoch after epoch. I'll change the value based on the epoch that we are running. And it requires a one line change to the whole algorithm. And I will now show you the code very quickly for incorporating the learning rate decay after every epoch. See, this is the abiding equation. You see it on the screen. The learning rate for a particular epoch is the learning rate which was originally there. This is the original learning rate by 1 plus decay. The decay is some small number, 0.001, times the epoch. Epoch is which epoch are we running on. So as the epochs increase, this number continues to grow. And as this number continues to grow, the overall learning rate, which I'm going to use in my equation, goes on reducing. Okay, as epochs go on increasing epoch, reducing learning rate. Okay, that's the basic intuition. So as I move closer and closer to my targets, as more and more epochs pass, I keep on reducing my learning rate. Okay, smaller steps. So now with that thing, let's just quickly look at code. It is a minor change to the code to get here. Okay, so here it is. This is mini batch with learning rate decay. So most of the code remains the same. In fact, all the code remains the same, except when I am applying. When I'm just show me the training loop. See, there is this whole thing. If you want to know, this learning rate for every epoch is equal to initial learning rate divided by 1 plus decay into epoch. So this is the equation. Learning rate epoch is equal to initial learning rate. This is to be used in our equation. So now look at the loop. This is the training loop for epoch in range. So we are going through all the epochs. At the beginning of every epoch, we are computing a new learning rate. That's all. This decay is a parameter which is defined somewhere else. It's a constant. Okay, it's 0.001. It's a hyperparameter. So this is the only line where change, and obviously where I use learning rate, I should use this current learning rate in my equation. So when I'm doing the accumulate gradients, you will see there. Go down. Sorry, when you say apply gradients, in place of learning rate, you will pass current learning rate as a parameter. Rub the. Yeah, you can go there and see the change. We are just taking you to the change which we did. Again, as I told you, this is same forward propagation, backward propagation, accumulating the gradients. Only here. Okay, just one word change. When I say apply gradients, I say network gradients. Only this learning rate is current learning rate of that epoch changes for every epoch. Epoch is basically one full traversal through the data is called an epoch. We go batch by batch. We don't do any change per batch. Only after every epoch, we drop the learning rate. We reduce the learning rate by the formula which I just showed you, so that the impact of the gradient is lesser and lesser. That's it. Rest of the code remains the same. Okay. So no, initial learning rate is also fixed. Sai Shivani. Initial learning rate is generally, let's say 0.9 or something. You can choose it, and then it keeps coming down. It's not a random value. It's a hyperparameter. So it's a fixed value. It's a tunable value, not a random value. Weights have random values. Neither mu nor learning rate have random values. No, both have fixed values which can be changed. They are called hyperparameters. The initial. Okay, so we are done. We have covered backward propagation. About 89 students have survived. Okay. Well, we expect that only. That is where the premium is. Okay. So in the next session, we start with the PyTorch, which is fairly easy to understand. So please go through these series and do all that. We can share you the code. Yeah, why not? We can share it in the group. We can give you. But honestly, the code has come from ChatGPT only. It's not our original code. We gave exactly the same prompt. We said take the backpropagation code from that Jason Brownlee. Add first stochastic. Add first mini batch. Then take the mini batch code. Add to it momentum. Take the momentum code and add to it learning rate decay. We did exactly that and we got that. We started with the Jason Brownlee code. Okay. So you can look at it and do it. Okay. So hopefully I have at least a certain number of people. I was hoping about 100 people would understand this, but I'm not sure. So, okay. But one criteria for our finishing school, sorry, for our research school, which is our internship program and for incubation, we will have a test which covers this, which I'm covering on Sunday, will become part of that. Because if you can't follow that, you'll be a waste of time in incubation and all that. You are definitely not cut out to be premium person. You are good enough for the lower levels, but not that. So we will be very particular that everything that I cover in this becomes a criteria for selection. Okay. So there we are. And okay. So, okay. So with this, we come to an end of the backpropagation series. We will now go to the programming series. We'll now start using Tantric. We did a few simple things with Tantric, but now we will do regular code. We will do the basic training of a network using PyTorch. And see, if you have understood this, understanding what happens in PyTorch becomes that much more easier. It becomes actually trivial, not just easy, it becomes trivial. You will see, and I'll connect this code with the PyTorch code that we talk about in the next Sunday.